Our focus today is on distinct lineage of microprocessors, one that fundamentally deviates from the common silicon playbook established by the West.
This is the Elbrus 2000 architecture. It is more than a standard CPU. It represents a story of national technological ambition, tracing its roots back to Soviet era supercomputing projects. Architecturally, it operates as a total outlier.
This divergence is evident in its adherence to the VLIW paradigm. While global competitors adopted superscalar and out of order execution, the Elbrus team deliberately maintained this statically scheduled model.
The distinction is critical. Standard chips attempt dynamic scheduling at runtime, consuming vast transistor resources. VLIW shifts this burden entirely to the compiler. This static strategy allows the processor to package up to 20 independent instructions into a single, massive 512-bit wide command for simultaneous execution.
To understand the performance dynamics, we must examine VLIW mechanism versus traditional superscalar design. In a modern x86 chip, complex hardware handles decoding, dependency checking, and the speculative execution, incurring
Elbrus
significant
eliminates
latency
that
and power
complexity.
cost.
Its data path is fundamentally simpler and strictly in order. The heavy lifting is done pre execution by the compiler, which identifies independent instructions and bundles them into a wide command.
This reliance on static scheduling places the burden of ILP extraction entirely on the compiler. This introduces a critical architectural dependency. What is the key drawback here?
That is the VLIW's Achilles heel. Performance is totally compiler dependent. If the compiler cannot extract high level parallelism, the overall performance degrades significantly. However, when optimally scheduled, the processor can execute those 20 operations in a single cycle.
Pragmatism drove the instruction set design, specifically the requirement to run legacy x86 software. This led to a mandatory key feature, x86 emulation.
This capability is implemented via Dynamic Binary Translation (DBT). It is a hardware level virtualization that translates x86 instructions into native VLIW code on the fly, a feature crucial for seamless transition from legacy infrastructure.
Beyond the parallelism, the architecture's defining the characteristics is its emphasis on hardware level security. How is this enforced at the lowest level?
It is managed by the Secure Computing Technology (SCT) system. This mandate means that in an E2K ISA, every pointer has explicit type information attached, acting as a mandatory security tag.
This is a key differentiator from the commercial processors, which typically manage such risk via softwares. Regarding the memory hierarchy, what is its composition?
The hardware checks the pointer's type and destination with every cached memory access. If the program attempts to access memory outside its authorized security domain, the processor immediately traps the access. This guarantees a physical, low level defense against common memory exploits.
To illustrate the security model, a common vulnerability like a buffer overflow is managed at the hardware level. What is the mechanism for blocking such an exploit?
Early chips featured 64 KB L1 and 256 L2. Modern multi-core chips such as Elbrus 16S scale significantly, incorporating up to 32 MB of shared L3 cache and leveraging multi-channel DDR4 controllers for the necessary through-output to match the chip's ILP.
The architecture has successfully scaled to modern multi-core configuration featuring up to 16 and even 32 cores in a newer concepts.
These designs incorporate significant NUMA non-uniform memory access support, allowing the high ILP of the VLIW core to multiply effectively across the chip for high-performance computing tasks. On raw metrics, particularly clock speed and floating point peak performance, the Elbrus chips lags. For example, a modern Elbrus chips might peak at 1.5 teraflops, while leading x86 X-forward chips surpass 35 teraflops.
The clear vision is high parallel throughput for specialized use. However, a comparative analysis requires us to address the question of raw performance relative to global leaders like Intel and AMD. The root cause of this performance lag is in architectural VLIW constraints, but rather the execution environment.
Elbrus signifies the endurance of a strategic sovereign technology strategy. The key comparison is with Intel's similar VLIW pursuit Itanium, which was commercially discontinued. Elbrus survived because it was mandated and because it offered critical security guarantees, specifically pointer validation, that commercial off the shelf chips often lack. The Elbrus 2000 is a unique case study, prioritizing reliability and national control over absolute peak performance. Its survival provides valuable insight into the challenges and necessity of sovereign technology strategies in a globalized supply chain market era.